Hello everyone. In this video, I will go over my solution for the problem named Happy Birthday 2 taken from Atcoder. This problem is an excellent problem which teaches you the pigeonhole principle, an important combinatorial idea which is not necessarily tested in ZCO, but it is nonetheless an important idea which you should have basic familiarity with. And it also teaches you complete search using bitmasks, which is very important for subtasks in ZCO, and it frequently shows up. So in this problem, we are given a sequence of n positive integers, a1 through an. We need to determine whether there are two subsequences, b and c, of the original array A, such that the sum of the elements in the two subsequents are equal modulo 200, and the two subsequents are different from each other, which means that there is at least one index I going from 1 to n where that index I is present in B or not present in C, or the other way around, it could be present in C and not present in B. Basically, when you consider two subsequences, they should not be the same, because like obviously if you consider two subsequences which are the same, then the elements will be the same, and so that's why the sums will be the same modulo 200. So that's a trivial example of two subsequences which have a sum modulo 200 which is the same, and that's why we don't want that trivial example. We want to like actually find two separate subsequences which have the same sum modulo 200, and we need to do this for n going up to 200 and ai going up to 10 power of 9. So let's look at an example. Let's say that these are the 5 elements in the array A. Then one possible example of a valid pair of subsequences is the number 180 in one subsequence and 189, 191 in another subsequence. And you will realize that if you do 189 plus 191, you get the number 380, which is congruent to 180 modulo 200, and that's why these two sums have the same value mod 200, and that's why we can print this as a solution. And in the next example, we can see that 123 and 523 are the same modulo 200, and that's why we just print yes, and we print this is the subsequence and this is the subsequence. And in the next example after that, there are no subsequences which satisfy the condition, so we'll print no. Just an important note that mod means the remainder when you divide by a particular number. So you don't need to know too much about modular arithmetic. Just know that when you divide two numbers, modulus is the remainder. And also note that the input and output formats are in this manner. So you should have obviously basic experience of and comfort in input and output. Now let's look at the key ideas involved in the solution. So one key idea involved in the solution is that we are working with remainders under 200. This means that whenever we consider the sums, we want the sums. We know that once we take the sum and once we take the remainder when it is divided by 200, the number which is left will be less than or equal to 200. So the remainder is always going to be less than or equal to 200, and this is the first key idea. The remainder will actually be less than 200, will be between 1 and 200. So it will be between 0 and 200, and this helps us because there are only 200 possibilities for the remainder. What this means is that there are only 200 possible values of the remainder modulo 200, and basically this implies that if you consider, if we find greater than 200 subsequences, then at least two subsequences will have the same sum. So this is actually the pigeonhole principle, and this is actually a very logical thing to conclude, because you know that there are only 200 possible values of the sum, and that's why if you consider 201 or 202 subsequences, then all those 201 subsequences cannot have separate values of a sum. They all cannot be distinct sums. There has to be a repetition because there are only 200 possibilities. So this observation which we form comes from the pigeonhole principle, but you obviously don't need to know the name. You can just realize that this is basic common sense, and this pigeonhole principle will help us because we know that we just need to find out a given number of subsequences, and once we manually in a brute force or a complete search manner, once we find a number of subsequences, once we find 201 subsequences, then we know that at least two of them will have the same sum, and we can just print out those two subsequences. So how exactly do we find out these number of subsequences? So in order to find out these subsequences, we can realize that a subsequence. So let's just recap what we need to do. We need to find 201 or more subsequences and store and basically store those subsequences corresponding and store the sums of those subsequences, so that once we get a repeated sum, we can just print out which are the two subsequences which have that same sum, and hence we find out what B and C are. So let's try to find out a way in which we can generate. Therefore, we need a way, an optimal way to generate more than 200 subsequences. So in order to generate subsequences, you can use bitmasks, and this is the second idea of the video. So how exactly do we use bitmasks in order to generate subsequences? So the key idea for iterating over all subsequences, or for iterating over a number of subsequences using bitmasks, is to realize that the value 2 raised to n indicates some bitmask stuff going on, and for n less than or equal to 8, we can generate all 2 raised to n subsequences using bit manipulation. So the way in which we do this is to set for all mask going from 0 till mask less than 2 raised to n and increasing mask by 1. What we will do is that we will check whether, so this is the mask which is the bit masks, and if mask, so for all I going from 0 to n, we will check whether the ith bit is set in mask. So if the ith bit is set in mask, then we know that the ith bit is a set bit in the value of mask, and hence we know that the ith element is included in this bit mask. Note that 2 raised to n is the number of subsequences because each subsequence can either be included or not included, and by the multiplication rule you can just multiply 2 n times to get 2 raised to n. And also note that this bit manipulation can be used because if you consider an example where n is 3, for example, then let's just say that these are all the numbers written in binary representation. So 0, 1, 2, 3, 4, 5, 6 and 7. So these are the numbers. Mask is going from 0 till 7, and for each bit going from 0 till 2, because n is 3, so I less than n means n goes up till 2. We will check whether mask and one left shifted I. This basically means that if the ith bit is set, if the ith bit in mask is set, this implies that index I is included in the subsequence, and that's why in this brute force manner we can check whether we can basically generate all the subsequences, because we are basically iterating through all the possibilities of an element being included or not. So for example, the zeroth element will be included in all the even cases, and it will not be included in the even cases, and it will be included in the odd cases, and so on for all the other elements. So in this manner, you can see that all possible combinations of an element being included and an element not being included are being considered. So you can divide this up into various combinations and realize that basically all possible subsequences are being generated, and hence this method of generating all possible subsequences is reliable, and we do this using Bitmasks. So this is a common technique. If you still didn't fully understand this, you can write that in the comments, or you can also search more about Bitmasks and iterating through all subsequences on Google. There'll be many useful resources. So now let's consider how we can use this technique of generating all possible 2 raised to n subsequences in order to solve the original problem of generating 201 or more subsequences. So we realize that we have found a way to generate 2 raised to n subsequences for a given n. Now let's just set the value of n to be equal to 8 in order to basically generate 2 raised to 8 subsequences. Note that if n is less than or equal to 8, we can just iterate all the subsequences. Otherwise, we can iterate 2 raised to 8 subsequences, because we know that 256, which is 2 raised to 8, is greater than 200, and hence by the pigeonhole principle, which is the same logic which we used uh, over here. So just by the pigeonhole principle, we can find at least 2 subsequences having the same sum. So that's what we will do. What we'll basically do is set the value of n to be equal to 8, and then we will generate 2 raised to 8 subsequences. And once we set 2 raised to 8 subsequences, we will also maintain what is the sum of each subsequence, and we will also maintain the set of indices in the subsequence corresponding to a subsequence with that corresponding to the sum. So what I'm basically saying is that we will maintain an array of size 200 which stores the subsequence of indices which have a value corresponding to that sum. So let's call this vector answer, because in the end we are answering by printing the subsequences. So answer of I is the set of indices, set or subsequence of indices with sum equal to I, with sum of I. And this basically means that whenever we iterate through the subsequences, we will also update the sum, and we will update the answer of that sum to be equal to the set of indices which have their bit set. So basically, if you want me to write the entire pseudo code, I will initialize answer to be a vector of size 200, because I can be up till 199. So the size of the vector will be 200. And what I'll do is, for each mask going from 1 till mask less than 2 raised to n, I go from 1 because we want the set of indices to be non-empty, and that's why we will uh, go for mask up till the from 1 till the value of 2 raised to n. We can actually just set this value to be 200. We don't need to uh, set it to be 2 raised to n, or we can set it to be the minimum of 2 raised to n comma 200. Either ways it works. The reason why we need to set it minimum of 2 raised to n comma 200 is because there can be 2 raised to n subsequences, and if n is something like 5 or 6, then we can only iterate for 31 elements, 32 elements, or 64 elements. That's why we can set mask to be the minimum of this, and then we will increase mask each time. And what we will do is we will maintain the sum. So the sum is 0, and for each I going from 0 to n, since we are using 0 based indexing, we will if you use bun based indexing, then the bits will change, because note that the bits are all 0 based indexing, and that's why it's optimal, that's why it's simple and not confusing to just use 0 based indexing for a complete search type of problem. So especially where you use bitmasks. So we will iterate for all I going from 0 till n minus 1. If the bit is set, then we will, so this is the way for checking whether the bit is set. If mask and one left shifted I, we will increase sum by a of I, and we will we'll do this first. In the end, we will check whether, so if answer of sum is empty, so if it's empty, then we know that there is no subsequence which has a sum equal to this. So what we will do is we will also maintain a vector car. So we will also maintain a vector car which represents the set of indices. And whenever we know that an element has been added, we will also uh, we will also push back that index I to car. And once we do that, we know that car represents all the indices which have which have their bit set and which are included in the mask. So car stores all the indices in the mask, and sum stores the sum of all the elements in that mask. And now we know that uh, we know that car is a representative of all the indices in the mask, and sum represents the sum of elements in that mask, and answer of sum represents this value curve. So that's why if answer of sum is empty, we will just set answer of sum to be equal to curve. Otherwise, we know that we have found the answer. So we have found two subsequences. So we have found two subsequences which have the same sum. And the reason why we have two subsequences with the same sum is because one subsequence already exists in answer of sum, and the second subsequence is cur. So answer of sum stores one subsequence and cur is the other subsequence, and that's why we will just print cur and we will print answer of sum. So we will print these two subsequences in the format given in the output section. And once we do this, we will just print yes as well. Otherwise, once we do the brute force for like 2 raised to n or 200 subsequences, and we have not found any pair of subsequences which overlap, then we know that, so this has to be 201 because it has to be greater than 200. So we'll set it to be 201. And once we have enumerated all these subsequences, then we can just print no, because we know that there should be a pair of overlapping elements. For safety, you can set it to be something larger, but in general, like any number which is much greater than 200 should work. Like 2 raised to 8 is actually 256, so 256 is also fine. But the general idea is that if n is small, then only it should not work. If n is big enough, then by the pigeonhole principle, there will exist a solution. And that's why basically we are printing no whenever n is small and there is no subsequence, that there are no two subsequences with the same sum. So now I'll show you the code which implements the same idea. So in the code, I use LL for long because AI can be up to 10 power of 9. Note that the actual sum modulo 200 will be less than 200, but we will still store the variables using LL. Then answer will represent the set of indices with sum equal to I, and we should use zero-based indexing. So this is a mistake which I had made, and this is the correct input format, and we should use zero-based indexing. So E of n is the correct format, is the correct syntax, and we will take in the value of AI for each I going from 0 till n minus 1. Max n represents the maximum value of the number of elements, and we iterate from 0 till 1 left shifted max n. Another way to write this would be like 256 or something, which I had said, and obviously we will iterate from 0 till max n only. We will iterate only, so another way to write this is minimum of n comma 8. So you can write it like this, or you can set max n. Either ways it will work. So we will store the sum of all elements which have their ith bit set, and we will store the indices included in the mask. So if masked and one left shifted I, the index I is included in the set of indices, and uh, this basically implies that it's included in the set of indices, and we should update the sum, and we should also update the current vector, because cur stores the set of indices in the current subsequence, and we are enumerating 256 subsequences. So we are enumerating about 256 subsequences. It will be plus or minus 1, but yeah, there are about 254, 255 or 256 subsequences which we are enumerating, and this is much greater than 200, so we will be fine by the pigeonhole principle. If n is less than 8, so like it should be minimum of this comma 1 left shifted n. So um, minimum of 256 comma 1 left shifted n, we are enumerating about 256 subsequences, or 1 left shifted n, which is the maximum number of subsequences, which is the max number of subsequences when n is less than or equal to 8. So it can overflow, 1 left shifted n can overflow if n is like 200 or something, which is why it's good to have a global variable. That's why max n was there in the first place. So we can set it to be the max mask. The max mask is equal to 256, and if n is less than or equal to 8, we will just set the max mask to be equal to 1 left shifted n, and mask will go from 0 till less than the max mask. So this is a better way to write this. Otherwise it can overflow if n is greater than 8, and you'll get all kinds of problems. So that's why you should just manually set max mask and iterate up till the maximum bit mask. Now once you check which all indices are included in the current subsequence, you will use those indices to print the answer. So if answer dot empty, if answer is not empty, then we will print yes, and we'll print all the indices. So print all the indices included in the set of indices with sum equal to sum, basically with sum equal to sum, and uh, also print the current set of indices, because they are the second subsequence with the same sum. And this in this manner we can check for uh, all the indices. We can basically print the two subsequences with the same sum. Otherwise we know that answer of sum should be updated to the current subsequence, because the current subsequence uh, has sum equal to sum and has indices in the vector card. So that's why we update answer of sum. And just to remind you, answer of I shows a set of indices with sum equal to I. And in this manner, we are ensuring that we are printing the two subsequences, because we are basically storing all the indices which have a sum uh, equal to this variable I. So in this manner, we can basically iterate through a number of subsequences greater than 200, and we can check whether two subsequences have the same sum. If this condition, if you reach the end and if you have not yet printed no, you have not yet printed yes, then the answer will be no, so you print no. And now I'll just submit this code to see that it gets accepted. So there were two mistakes which I had made in my code. One mistake was to not realize that we need to print the indices in the correct format. So we need to print the values. We need to first print the size of the vector answer of sum, and we need to print the size of the vector curve, because we need to print the size of the two subsequences before printing the actual subsequence. Another mistake which I made was to not realize that we are using zero-based indexing in our brute force method, in our complete search using Bitmasks, That's why when we print the two subsequences, we need to print them using one base indexing. So we need to increase one to the indices, and then this code basically gets accepted, which makes both the changes of printing using the correct format and printing one base indexing. So I hope you got a good understanding of the solution and of the techniques of pigeonhole principle and complete search using bitmasks used in this problem. You are almost guaranteed to get at least a couple of subtasks in ZCO, or at least one subtask worth a number of points, which uses the principle of brute force, uh, and maybe which uses bitmasks in order to do the brute force. So you should solve more problems on this topic. And I hope you like this problem and my solution. If you have any doubts, do leave them in the comments down below. And stay tuned for more videos on related topics.